So hello everyone. So in the last class we have seen about the propagation delay derivation, that how to derive the propagation delay tau PHL and tau PLH, right? And then we have seen that what is the process to do that. So basically if we just revise it for time being, then we can see that in the initial stage our MOSFET NMOS, because we are considering the discharging scenario. So in the first half NMOS works in the saturation region, and then later on it works in the linear region. So substituting those equation of the linear region and the saturation region currents, we find the limits, we find the formula for this our propagation delay after putting the integration limits and solving it. So this is what it is. Now, as I have told you in the last class, that in the next class we are going to see some numericals based on it. So today we are just going to see them. There's numericals, right? So let's try first numerical based on this, our whatever we have seen in our last class. So based on that, we'll try to see a numerical. Not only a numerical, but like to see 2-3 numericals today in today's class. So you see the first numerical is related to your for this particular figure which is given in the this diagram. So this is nothing but an inverter. So in this inverter the VDD is 3.3 volts, right? And the IV characteristics of the NMOS transistors are specified. Okay, so here the drain characteristics are given in words rather. So what it says, I mean whatever this is given in word statement, so we'll try to plot the characteristics according to the statements, and then we will see that what we can understand from that. So that will be helpful to you. So you see when VGS is equal to so VDD is given as 3.3 volt, and the IV characteristics of the NMOS transistor are specified as follows. So when VGS is equal to 3.3, so let me first plot here that if we try to plot the characteristics of our NMOS, let's say, so if I plot the in small, I mean if I plot the characteristics, so then you can see that here I take the drain current. Okay, so ID will be here on the y-axis, whereas on the x-axis it will be VDS, right? And for different values of VGS, we plot this drain current. So you see how we do. So this in the numerical it is written that when VGS is equal to 3.3 volts, so VDD is basically 3.3 volts. So this is what the maximum voltage at the input which you can apply. So this is our input and this is our VDD. So this is given as 3.3 volt. So at the input we can apply maximum equal to VDD volts. So VDD is 3.3. So we can apply at the input 3.3 volts only. So you see, so it is written that for VGS is equal to 3.3 volt. So the characteristics will be somewhat like this. Okay, for 3.3 volt. So it will be the maximum current. So at this particular thing, so this is for VGS is equal to 3.3 volts, right? So it is 3.3 volts. So for this 3.3 volts, if I see, so then you can find easily that and this is VDD on the x-axis. So you see what does this says. So the drain current reaches its saturation current level of 2 milliamperes. So you see this particular current level is your approximately 2 milliamperes. Okay, so this is 2 milliamps. For VDS greater than 2.5, so it says that for VDS greater than 2.5, so VDS is somewhere, let's say at this point it is reaching saturation. So your VDS is equal to 2.5 here. So this is our x-axis. So this VDS is 2.5 here on the x-axis. So you see this voltage is given as the saturation voltage. Okay, so at which the saturation is reaching. So assume that the input signal is applied to the gate is a step pulse. Okay, So the input is the step pulse that switches instantaneously from 0 to 3.3 volts. So this means that the waveform, the input waveform, do not have any rise time. Okay. So using the data above, calculate the delay time necessary for the output to fall from its initial value. So using the data above, calculate the delay time necessary for the output to fall from its initial value of 3.3 volt. So the output is falling. Okay. So initially it is at the stable value was 3.3 volts, and now it is falling to, we have to calculate this particular time, the delay time, when the output falls from the steady state value 3.3 volts to 1.65 volts. So 1.65 volts. So if I like half this 3.3 volts, so we'll get 1.65 volt. So basically in the question asks about the tau PHL. Okay, so high to low. So the output is, so input is rising from low to high, so output will fall from high to low. Yes, using the data above, calculate the delay time necessary for the output to fall from its initial value. So output is falling, so we have to find tau PHL, high to low. Okay, so you see, when the input is rising, so we have to find the output will fall. So we have to find that. So assuming an output load capacitance of something, so that is not, I cannot see that, but it is given something. So let's say it is some value, probably it is 300 femtofarads. So okay, we assume that as this is particular thing. Now from this thing, this is the scenario. So in this problem, as if we see our drain current equation, so we can find easily that in the drain current equation, although we have other things, but we cannot see the threshold voltage of the NMOS, because for the discharge particularly, because the output is falling, so the capacitor is discharging basically, right? So for the discharging case, if we have to find, we want the threshold voltage of the NMOS, so that is not given. So point is like how we can find that threshold voltage. We can find that with the help of basically this equations, this characteristics which are given here. So as we know that our saturation region occurs when VGS is greater than VGN, so I am not going to write that, but the other condition is when VDS is greater than or equal to VGS minus VTN. Okay, so this is what the case is. So you see, saturation is reaching at 2.5 volts. So when VDS is equal to 2.5 volts, at that time your saturation is reaching, and at that particular time your VGS is 3.3 volts. Okay, so you see, we from this equation basically we can find the threshold voltage of the NMOS directly. So threshold voltage of NMOS will be VGS is 3.3 minus this VGS. So okay, or you can write VGS minus VDS equal to VT. So VGS is your VGS is 3.3 volts and VDS is 2.5 you have applied. So 3.3 minus 2.5. So 3.3 minus 2.5 will give you something like 0.8 volts. Okay, so you see VTN for this particular thing will be your 0.8 volt. So if you understand this basic thing of like what is your VTN, then things will be easy for you, because this particular thing is not given. Okay, so then the other important thing is that we have to find that our transistor works in which region. Okay, so that is again the important thing, that when the output is falling, that at that time our transistor works in which region. So let's see if you want to find it out. So how we can do this? So you see, I'll show you in the next slide. So you see basically what is happening. Our transistor is, as our output is, let me show it here. So as our output is falling, so you see this is our input and this is our output. So output is like say falling this way. So we have to find that our this is our VDS. Okay, so this is our VDS. So VDS, and this is my ID, right? So it is falling, so output is falling. Oh sorry, No, this is not the case. So you see, so as output is falling, so if I plot this particular thing here like this, sorry, so if I plot this characteristics like this is my y-axis and this is x-axis. So on the x-axis I'll take time, because I want the characteristics, we have to find the delay, so we want time, so we'll plot time on the x-axis, whereas the output voltage vout is on our y-axis. So if I plot this, so you see basically what is happening, it is falling. So previously at the initial at the steady state, during the steady state, the output was at some voltage which is 3.3 volts, okay, and then it is falling, let's say, okay. So we have to find that up to certain voltage, okay, so this is what the case is, so it is falling. So you see, this transistor NMOS will operate up to some point in one region and after that point in another region. So how to find it out, in which region it is operating? So just to find that, what we have to do is we have to use our this conditions of drain and this linear and saturation region. So if our input is connected to VDS, okay, so you see our VGS is given as 3.3 volt. So VGS is connected to 3.3 volts, right? At that instant when the switching starts. And VDS Vout was initially 3.3 volts and now it is falling. So when VDS, when you apply input 3.3 volts to the input and the output is at the 3.3 volts. So you see drain to source and gate to source voltages are both equal. So if both the voltages are equal, then obviously if you check the condition, VDS should be greater than VGS minus VT, okay, for your saturation region. So if you see this condition, if your VDS and VGS are equal, this condition will always be true, that VDS will always be greater than your VGS minus VT. So VGS is 3.3. So if you subtract let's say 0.8 volt, which we got the threshold voltage, so if you subtract 0.8 volts from 3.3 volts, so this VDS, which is initially 3.3 volt, so the condition will be that the transistor will work in the saturation region, okay. So the point is that when the switching starts at this point, basically, so the transistor works in the saturation region at that point. And you see, up till a certain point which I have made here, the transistor will keep working in the saturation region. Why? Because let's say at this point particularly, this point is equal to VDS is equal to VGS minus VT. So up to this point, and here in this case this point is 2.5 volts, okay. So till the time the output falls to the value of 2.5 volts, the transistor will keep on working in the saturation region. So the transistor NMOS works in the saturation region from 3.3 volts to 2.5 volts, okay. So during this region the transistor will work in the saturation region. Thereafter from 2 volts onwards it will work in the linear region, okay. So we have to find this delay time. So we'll see that how to find it, okay. So I hope with this diagram, although it is not very clear, but I've tried to explain you the things so you can understand this, okay. So you see the same thing which I have told you will apply here. So you see in the solution, what we do is our NMOS transistor, as I have told you at the from the beginning of this transition. So let's say that time is t is equal to 0, okay, to up to certain point t1 dash, the transistor works in the saturation region. So that t1 dash will come when your output voltage is equal to 2.5 volts, okay. So that time is this. So during this region our transistor works in the saturation region. So we have to use the saturation current equation, and as our capacitor is discharging, so you have to use the equation C dV out upon dt is equal to minus of ID, because of this minus is because of discharging, okay. So then we substitute the limits of voltage and the limits of time, and if we integrate this thing and like substitute the limits and solve it, then we get that this particular time which we have denoted the time during which the transistor will work in the saturation region. So you see this in this equation, this VTN is equal to 0.8 is also used, and capacitor is equal to 300 femtofarad is also used, and this 2 milliampere is given in the numerical, is given in the problem itself. So I'll use that 2 milliamperes. So if we solve this equation, then we get T saturation, and that much amount of time in which the transistor will work in the saturation region is 120 picoseconds, let's say. Okay, and so you see, this is what is clear. Now we have to find the other thing, which is our the linear region. So the transistor will operate for some time in the saturation region, in the linear region as well. So our total delay time will be total propagation delay time will be the sum of these two. Okay, if you want to find the tau PHL, then high to low, then it will be the sum of the 50%. Okay, so it is the 50% transition from the of the input to the output. So that much time. So it will be sum of the portion in which the transistor works in saturation region, and the other region in which it will operate in the linear region. So the total delay will be the sum of this two time elapsed. Okay, so this two time which has elapsed in this case. Okay, so let's move on to the other equation, but probably in the other equation we have to we will require this Kn as well. So to find Kn, what we have to do, because the saturation current was already given, so we don't require Kn, okay, to solve this equation. But later on, to use the equation of drain current in the linear region, we will require Kn. So we can calculate Kn from this whatever is given to us. So saturation region current was given as 2 milliamperes, and if we solve this equation, which is the saturation current equation, so if we rewrite the equation in terms of Kn and solve it, so then we can easily find, because all the input all the parameters which are required to solve this equation are already we have found and we know them, so from the problem itself. So then you can see that your Kn is equal to this 0.64 into 10 to the power minus 3 amperes per volt square. Alright, so once you have found this, then later on in the other part you can easily find that the other portion in which the transistor will work in the linear region. So the transistor will work in the linear region from 2.5 volts, okay, so where it stops working in the saturation region, from that point onwards till the point of like Vt, this threshold voltage, this transition is at 50% of the output. So transition, the point at which the transition comes to the 50% is your 1.65 volts. Okay, so if you substitute the limits of 2.5 to 1.65 volts, and if you solve this equation, then we can find the other time. So let's denote that time as the time between T set to T delay. So after substituting the limits and solving the integration, what we find is the total current, because all the inputs, all the parameters which are required to solve those equations are already we have calculated. So if we solve this particular time, so then we'll get 133 picoseconds. Okay, so for 133 picoseconds, the transistor NMOS will operate in the linear region, right? Whereas for 120 picoseconds, it will operate in the saturation region. Okay, so the total propagation delay will be your sum of total tau PHL, okay, propagation delay of the falling side of the falling output will be your sum of 120 plus 133. Okay, so it is 120 plus 133, so sum of the two numbers, so 120 and 133. So your total delay will be 253 picoseconds, right? So I hope this is how you have to solve the things. Okay. And similarly, if in the problem tau PLH is asked rather than tau PHL, then we can accordingly calculate the things considering PMOS rather than the NMOS. Okay, so being the problem for tau PHL, high to low, because the capacitor is discharging, we have used what we have seen in the derivation. Okay. So I hope this problem is clear to you, and if any of you have any queries related to it, you can obviously ask to me in your comments or like in an extra class as well. Okay, so let's move on to the another problem, and this problem is also not that much difficult. It is also easy. So we'll cover this problem as well, and if time permits, the third problem, else we'll cover the third problem in the next class. Okay, So in this problem, this problem says that for the CMOS inverter shown in the figure, this 6.2. So this is basically I have taken from your book as well. Okay, so the previous example was also from the book, and this example is also from the book. So you can directly refer the book as well. Okay, and this is the example. But there in the book it is not given in that much detail. So I have tried to explain you the things. But if you have problem understanding here, you can refer the book as well. Okay. So for the CMOS inverter shown in this figure, given figure, so it is again an inverter, nothing new, with a power supply voltage of VDD is equal to 5 volts. So VDD is equal given as 5 volts. Determine the fall time. So in this question, we don't have to find the propagation delay tau PHL. We have to find the fall time. So how we have defined fall time? It is the time which is elapsed when the output falls from 90% to the 10% value. Okay, from when the output falls from 90% from its steady state value. So when the output falls from 90% of its steady state value to the 10% of steady state value. So that much time which is elapsed between these due durations is called your fall time. So you have to determine that in this question. So determine the fall time, which is defined as the time elapsed between the point at which V out is equal to, so that is what the definition is given. So if your supply voltage is 5 volt, so the 90% of 5 volts will be 4.5 volts, okay, and 10% of 5 volts will be 0.5 volts. So what we want is the time elapsed when the output falls from 4.5 volts to 0.5 volts. So that is what our aim is. So that much time we have to find. So use both the average current method and the differential. So the new thing in the problem is that we have to find the current. Okay, we have to find the fall time with the help of two methods. So both the methods which you studied. So one is the average current method and the other one is the differential equation method. Although we have not seen derivation for this fall time, but it is not difficult to find. We can easily calculate that with the basics which we have used to determine the tau PHL. Okay, same things. The only thing is we have to find that in which region our transistors are working. So you can find that we can easily, using the equations and the method which we have seen in the last example as well. You can find the any time, any transition time which is asked in the numerical. So here in this question T fall is asked, so you can find that as well. Okay, so you see, so this is what use both the average current method and the differential equation method for calculating tau fall. Okay, so the output load capacitance is 1 picofarad. So capacitance is given, C load is equal to 1 picofarad. The NMOS transistor parameters are given as, so mu n Cox is given as 20 microampere per volt square. W by L of the NMOS is given as 10, and VTN is equal to 1 volts. So basically in this numerical we have to find this fall with two methods. So after finding the this T fall with both the methods, we'll compare that how much difference we get. Okay, so first method, as I have already in the previous class I have told you that this is a very crude method. Okay, so it's a rough method, approximate, it gives you the approximate solution, and the second method gives you more accurate solution. Okay, so we'll see that how much difference is there between these two. So let's see how we'll solve it with the first method and then with the second method. So let's see with the first method. Okay, average current method. So you see what we'll do to find the average current. So you see, let me draw it here. So you see your input is, this is, let's say, my input voltage, and here I'll plot the output voltage. Okay, so this is output. So when your input is transiting, so let's say your input is transiting, let's say initially it is 0 and then it is becoming 1, something like this. Okay, yes, and your output was initially, let's say, this, and then it is falling. Okay, so we have to find this 90% to somewhere 10%. So assume that this is 90% in the 10% range. Okay, so these are the things, and we have to find this. So if you want to find the average current, okay, so average current is, you see, when your input has already transited. So this is your input. So input had made a transition. So when the input is like changed from 0 to some value, so let's say this is VDD. So when to find the average value of the current, we have to use this particular condition. When the input becomes VDD, at that instant particularly your output is also VDD. Okay, so you see this output is also VDD at that instant. If you see the projections, let's assume this. So if you'll see the projection, so you'll see that the transitions are occurring at the same place. So we have to find this particular point. Okay, so you just see this, and then later on when the transition ends, at that time your input remains at VDD, but your output reaches to some other value. So it is say 10%. Okay, so you see this is what we have to see. So this is what I wanted to explain you. So you have to find the average of these two currents. Which two currents? When the input becomes 5 volt and the output is 4.5 volt, which is 90%, okay, of your this steady state value of the output. And the other value of the current which you have to take in the average is your, when the input remains 5 volt but the output becomes 0.5 volt, right? So the output is transiting from 4.5 volts to 0.5 volt when the input is at 5 volts. So I hope this is clear to you. Okay, sometimes people get confused in this, that why you have not taken V in is equal to 0, rather you have taken V in is equal to 5. So why it is so? So I have clarified that why we have done this, because we have to see the transition. So once the input has transited to its steady state value, then what happens to the output? Then only the output will start switching. So we have to use that, and as it is average, so that is why the half is coming there. Now there is nothing new. So you see the same thing which we have seen earlier. So during the range where of VDS is greater than VGS minus VTN, our transistor will work in the saturation region, and thereafter it will work in the linear region. So here in this case, as you have seen that your threshold voltage is what is your threshold voltage? So it is, threshold voltage is 1 volt. Okay, so here it is given that threshold voltage is 1 volt. So you see 5 minus 1, so 4 volt. Okay, so 4 volt. From 4 volt onwards, the transistor will start working in the linear region. But up to 4 volt, the device will work in the saturation region. And we have to find this 4.5 volt to 0.5 volt. So we have to again, okay, so this is what you see. If you see the 4.5 volt point, at that point, if you assume, so your transistor will work in the saturation region. Okay, at that point. Because here in this case, we are not integrating it over the whole region from 90% to 10%. We are taking two values at those particular instants, when the transition is at point or the 90% value, and the other point at which the transition and the voltage is at 10% value of the steady state value. So these 2 points, and then we'll take the average of this. Okay, we don't consider the whole transition, the intermediate values, okay, between the transitions. So that is why it gives you the approximate results. This is what the reason is. So we have taken these two values considering that the transistor works in the saturation region for the first half up to 4 volts. So at 4.5 basically it works in the saturation region, and at 0.5 volts the device works in the linear region. So substituting this two, writing these two equations, then things are not difficult. You have to just substitute the values from the data which is given in the numerical, and if we solve it, then we find that our I average is coming something like 0.98 milliamperes. Okay, then this is our average current, and if we use this average current to calculate our fall time, so then we know that our average current, this fall time is basically it is nothing but Q is equal to CV equation. So I have already explained that in the last class. So substituting those things, you can calculate the fall time, and it comes like 4.05 nanoseconds. So this is the fall time, which is very easy to calculate if you can find that at those particular points your transistor operates in which region. So if you find that correctly, then it is nothing. You can find those values and then substitute them the data in the equations and get the value. So it is the method is very easy. So okay, but the second method in which you have to find the same solution, fault time, but now with the help of differential equation approach. So again we have to do the same thing, but for the whole range. So what we have to do is, again we will write this equation. We will use the CdV out upon dt equation, and which is equal to our minus of id. Okay, so discharging current. So our NMOS, as I have told you, that the NMOS operates in from 4.5 volts to 4 volt. It operates in the saturation region. So that is what we are going to do here in this equation, substituting all the other values. See, this is the current equation which we have used, and if we substitute this particular thing and solve it, okay, in terms of this dV out, because if you substitute the drain current equation, so okay, we'll get the equation in terms of dV out. So if we integrate it between 0 to T saturation region, the transistor, the voltage ranges from 4.5 to 4 volt. So during this region, the transistor operates in the saturation region. So that much time is your 0.3125 nanoseconds after solving this, substituting the values. It's easy. Then later on, from 4 volts to 0.5 volts, the transistor will work in the linear region. Okay, so substituting the linear region equation, current equation, okay, and then rewriting the equation in terms of dV out and dt, okay, and integrating it during the these two ranges. And if we solve it, then we find that the other region in which the transistor works in your linear region is this value. So it works in the linear region for this much time. So 3.385 for 3.385 nanoseconds, it works in the saturation region. Okay, in the linear region, sorry. Whereas for 0.3125 nanoseconds, it works in the saturation region. So the total time, if you have to find, so it will be the sum of these two. So if you sum them up, 3.385 nanoseconds and 0.3125 nanoseconds, so we can find the total fall time. So the total fall time will be your 3.6975 nanoseconds. Okay, so you can see that this is what you have found by the second method, by the differential equation method. In both the methods, you have to identify in which region your transistors are working. In the first case, you take the average of these two. In the second, you integrate it over the whole range. Okay, so you consider the intermediate values as well. So that is why the second method gives you more appropriate result. Okay, so this is better than the previous one. So but if you want to see that how much difference is between the two values, so then you can see that this is 4.05 nanoseconds fall time from the first method, and from the second method it is coming like 3.6975 nanoseconds. So if I just see that this by the first method, how much wrong, how much, this is your exact, let's say 3.6975, so it is how much above than this 3.6975 nanoseconds. So if you see, then you can find that it is approximately 10% higher. So by the first method, you found the result as 10% more than, 10%, the value is 10% more than the other method. Okay, so this is what it is. So it and you see this they are approximate, so 10% is not a much difference. So for hand calculations, for manual calculations, you can use the first method as well. Okay, if you are designing the things and we have to calculate that approximately how much current will flow, then how much time it will take, okay, for the transition, for the fall time, then you can calculate very easily by the first method, because by that method it will, although it will give you 10% more 10% more value, but it will save a lot of time. Okay, because the other method takes more time. So this is what the disadvantage and advantage of these two methods. Okay, so with this we stop our today's class here. We'll see the last problem, the next problem, in our next class. Okay, so thank you to all of you for listening. Thanks a lot.